Hey everybody, so let's try to make up for today's issues we had. First of all, this was me during break. As you can see, I had hit the briars pretty hard because I was grading the tests and I couldn't believe the confusion we had for endothermic and exothermic. So, question involved going from solid to gas, and was it endothermic or exothermic? And if you just think of this um, phase diagram where pressure is against temperature. We have temperature. Where's my mouse? There it is. All right. So temperature's down here. To go from solid to gas, you have to increase the temperature. And increasing the temperature means it's endothermic. You're adding heat to the system. You're adding energy to the system to make a solid into a gas or a liquid into gas. Going this way from solid to liquid, liquid to gas, those are all endothermic because you have to increase temperature. Going the other way, gas to liquid, liquid to solid, those are all exothermic. You have to take heat out. In fact, if you think of it more, look at this, right? So here is solid. And if I want to make that liquid, I got to heat it up. I got to endothermically make it into a liquid. And then when it's a liquid, I can endothermically add energy to make it a gas. You have to add energy to get these things moving around more. And so there we are at a gas. And that was a matter of putting energy in. To make this gas go back to a liquid, I have to take energy out. It's exothermic. I got to pull out that energy to make that gas more liquidy, to slow it down. Exothermic energy has to come out. And then to make that liquid into a solid, I have to do the same thing. It's exothermic. I have to pull energy out to make that a solid. So hopefully, between those two things, we've got this covered now. Um, and I can go back to avoiding ice cream. All right. Ionic, by the way, on your, we can cover that later, actually. All right. So we're talking about solutions. And solutions are like Kool-Aid coming through a brick wall. Solutions are homogeneous. We talked that homogeneous versus heterogeneous, which is a solution, and a solution would be uniform throughout, the same throughout. That's homogeneous. So it's a homogeneous mixture. There's two parts of a solution. There's the solute, which is the dissolved material. It's usually going to be a solid, especially for this week and a half. Examples are ionic salts, or your notes say of, but it should say or molecular compounds. All right. So those are the types of solutes. Solvent wise, it's the dissolving material. Solvents are the dissolving material. We're usually talking about liquids, specifically for the next week and a half. And so water, alcohols would be the solvents that we're going to use. All right, so solubility. So solubility is the grams of solute that are dissolved by the solvent, and that can be zero. The golden rule of solubility is that likes dissolve likes. What does that mean? That means a polar solvent will dissolve a polar compound, and a nonpolar solvent will dissolve a nonpolar compound. Some examples, I guess, we'll just hit this. Some examples of polar solutes are ionic salts, where you have a metal and a nonmetal, a plus metal and a negative nonmetal. Anything that's hydrogen bonding is going to have that plus minus situation. They will dissolve well in polar solvents. Water is considered the polar solvent. And we'll look at that in a second. Non-polar solutes, you looking for things with many CH bonds, the diatomics, the Magnificent Seven, or what we call Brinkelhoff, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. So Br2, I2, N2, Cl2, H2, O2, or F2. They share electrons equally, so they're very nonpolar. I don't love that myself. CH bonds is more important. If you have a lot of CH bonds, you're very nonpolar. Let's take a look at this. What's happening here? So here is a ionic compound. You have the minuses and the pluses. And water is able to break this up because water has plus hydrogens and negative oxygen. So the plus hydrogens will pull off the negative, and the negative oxygens will pull off the positives. And that's how this dissolving happens. This is attraction of pluses and minuses that pull apart this solid. So that is why likes dissolve likes in this case. If you have a nonpolar compound with a bunch of CHs and you put it in nonpolar solvent, there is no plus minuses to get involved here. So it can just all sort of, it's what we say in the business, sort of fat and dissolving fat, basically. So oily substances will dissolve in uh, solvents that have no polarity to them. So there's no charges to get involved here. Molarity. So we talked about molarity. So the quantitative description of molarity, it uses numbers. Molarity is defined as the moles of solute, so the moles of solid, in liters of solution, of total liquid solution. So the equation for molarity, which is capital M, will be the moles of the solid divided by the liters of the liquid. And qualitatively, concentrated things will have a high molarity, and hopefully you learned this in the PhET. There's large amounts of solute or solid, and it's near a point of near or at saturation that would be concentrated. And you know this from your making Kool-Aid, making hot chocolate, making a solution that you would drink. The more stuff, the more sugar you put in it, you're going to have a higher molarity. It's going to be very concentrated. It's going to be very sweet. Whereas dilute means low molarity. If you put a whole bunch of solvent, a whole bunch of water in your Kool-Aid and not a lot of sugar, a whole bunch of water in your Kool-Aid, in your hot chocolate and not a lot of hot chocolate mix, it's going to be very dilute. It's not going to particularly be very sugary tasting. It's going to taste more like water. So those are just two words, concentrated and dilute, which you should be familiar with, but if you aren't, there they are. So let's talk about miscibility. So here's a chart that is in many labs, and this is a miscibility chart. And what it tells you is, will these liquids mix? And miscible means mixable, forms a homogeneous solution when combined. So it's a like plus a like. So let's see here. If we look at the red things, those are immiscible, and that forms a barrier. It's heterogeneous, the mixture when combined. So some unlike solvent and solute. So let's look at here. Dichloromethane does not dissolve in water. Dichloromethane has carbon-hydrogen bonds, and water, H2O, is, of course, the most polar of things. So they don't mix. And what you would see is a barrier between the two, like oil and water. Ethyl acetate in water, same thing. Heptane in water, hexane in water. So these are all non-polar solvents or compounds, and they're not mixing. They're immiscible with water because water is a very polar compound. Tetrahydrofuran, that's not entirely true. Toluene will not dissolve in water. And you see here, water will not dissolve in xylene. Water will also, just as it says here, not dissolve in these things. Acetone, interesting thing, here's acetone. Look, acetone actually dissolves everything. It dissolves water, it dissolves heptane, hexane. It's called a universal solvent. I know in this class we say water is, but acetone in a lab is considered a universal solvent because it can sort of straddle between the nonpolar and polar compounds based on where its polarity is. So anyway, this is just an example of things that mix and things that don't, and hopefully in a class I'll be able to show you some of that stuff. All right, and here's why it happens. If you have a nonpolar solid or material and you try to mix it with water, the water likes this plus minus thing going on, right? Here's your minus oxygen attracted to the positive hydrogens, and they get really into that. They love being attracted to each other, and these globules of non-charge can't really penetrate in there. They can't get into that party. So there is no dissolving, and you'll see a barrier, a heterogeneous mixture occur for that. All right, so I'm going to stop here and then start this next thing about solubility curves.